we're talking about doing question 1, which is Green's theorem. English guy came up with a clever idea that you can take a line integral of closed loop and replace it by a double integral. And the question that we're going to set up here is xy dx plus x squared y cubed dy. And C is a triangle, which I'm just going to draw because you kind of need to draw these things anyway. So 0, 0, so you start there. You go to 1, 0, which I'm saying is there. So you're going positive orientation, which means I do not need to do anything to my, there we go, 1, 4. I don't need to do anything to my integral because in the order that they gave me, would you agree that that is positive orientation, right? Now, if they'd said 0, 0, 1, 4, 1, 0, 1 and back again, right? If they made me go that way, the only difference would be when I stick a negative in my answer when I got it, right? So orientation just means your answer is different. So this is going to be my D, which is a triangle. I'm going to find this guy, take away this guy, and I'm going to do a double integral over this region D. So I might as well set up my limits of integration while we're at it. I think this one lends itself to type 1. And do you remember scanning left to right? That means x's are going to go from 0 to 1. And what are the y's going to be? Well, I kind of need to know the equation of this line. Well, it has a slope of 4 going through the origin, so it's 4x. So y is going to go from the bottom, which is a y value of 0, to the top, which is a straight line. Are you comfortable about the limits of integration and oops, where they came from? We good? Now, each of these bits is going to get changed. Let's see what we have. We're going to have a double integral from x equals 0 to x equals 1, from y equals 0 to y equals 4x. Differentiate this guy, because that's basically q and this guy's p. Differentiate this guy with respect to x, and you get 2x y cubed minus differentiate this guy with respect to y, and you get x, and y goes first, and x goes second. Right, can I leave that integral at that point? Because haven't we done tons of double integrals, and that's just some horrible polynomial, and you get whatever you get. Now, these questions ask you to do it directly, which would have been really a whole load of straight lines and parametric. So why don't you just do it Green's theorem and both answers are the same? So if this ends up being, according to them, at least it's 20, then make both answers 20 because it will be. So don't bother about doing it directly. Can you just trust me that Green's theorem works and you don't need to do it a second method to convince yourself that it works? Are we good? Right, so what are the main features? Draw the region so you know what D looks like. Set up limits of integration. Do the calculation, dy dx, and you're good to go. So next one, question 2. Do I need 2 or will I do 3? Let's see what yeah, 2's different. It's different enough at least. We're doing that guy. Y e to the x and dx plus 2 e to the x dy. That's good. C is described as a 4 point. So we're going to go from the origin to 2, 0. And then from 2, 0 to 2, 5. And 2, 5 to 0, 5. And then back home. Oh, it's just a big box, isn't it? So the limits of integration are really just going to be x's from 0 to what that number is. It's a badly drawn 2. And the y's are going to be 0 to 5. Okay, so that went pretty smoothly. So we're going to do a double integral from, who cares, x equals 0 to x equals 2, from y equals 0 to y equals 5. This is p, right? And this is q. So we're going to do the partial derivative of this guy with respect to x, take away the partial derivative of this guy with respect to y. And then we're going to do a dy and a dx. And something really nice happens. You get that, don't you? Is this one separable? Okay. Is this double integral separable? Can I do it in 2 pieces? Limits of integration are numbers. And is this thing separable? Yeah. So you would do e to the x from x equals 0 to x equals 2 dx. And from y equals 0 to y equals 5. If there's nothing there, you give it a 1 and off you go. And yeah, I think when they're separable, isn't it at least equal amount of work and probably less work? So I can't think of a situation where I might not do it. Right. And whatever that comes to is your answer. Okay. Here's 4. Oh, little notation thing. Did you notice that this one didn't have the little circle thing around it? Just careless. It doesn't change a darn thing. They should, I guess, have removed all of them, but for some reason they didn't. So this one doesn't either, but it's still a closed loop. And C is described as a circle, x squared plus y squared equals 16. So that's C. Oh, positive orientation, which is nice. Isn't D going to be the inside? I'm going to do a double integral. I'm going to do the derivative. Make sure I get these right. I almost get these guys wrong. That guy with x and this guy with y. And I'm just going to call it dA. The reason why I'm going to do this is that 2 things are happening at once here. I'm going to be differentiating these guys with respect to x and y, and they're going to fit in here. But when you see a circle and it's 2-dimensional, shouldn't you be thinking polar? So what's going to happen then is that the R is going to be from 0 to 2. And since it's a complete circle, as far as I can see, it's a complete circle, which it is. But I'll just check. Yes, it is. We got that. So I'm going to do from R equals 0 to R equals 2, and theta equals 0 to theta equals 2 pi. The dA is going to become R. I guess the way I've written it is going to have to be d theta dr. If you differentiate this guy with respect to x, you get -4 x squared. And if you differentiate, where's that 4 come from? That's a 6. And if you differentiate this guy with respect to y, you get +6 y squared. We'll double check on that. Is the signs right? The signs are right, except that is a negative. And so if you differentiate that, you're subtracting a negative. Oh, you do add it. Damn it. I wish I hadn't said that. So let me, there's my P, there's my Q. That guy's negative. And so is that guy. Double, treble check. That guy differentiated is negative 6x squared. That guy differentiated is 6y squared, but you subtract them. That's actually good news. Isn't this guy negative 6r squared? Show you what it looks like. Do it in a bubble. Negative 6x squared, negative 6y squared. Pull out negative 6 as a common factor. 6r squared, right? So we now have negative 6r squared times an r and a d theta and a dr. So we are going to be integrating negative 6r cubed d theta dr. I'm going to stop here. Couldn't you separate that guy out as well? Right, 0 to 2 of maybe just the r cubed and leave the 6 with the theta, or whatever combination you feel like. You get the same answer each time. Now, converting a line integral of a closed loop into a double integral, right, in this case, happens to be a circle, does involve less work, typically, than just doing it the old-fashioned way. If I had to do this the old-fashioned way, what I mean by that is turn everybody into t's. So when I have to find a parametric equation for the circle, so they're going to be things like 2 sine t and 2 cosine t, or 4 sine t, 4 cosine t, whatever it might be. You're going to have those guys and you're going to have to deal with them, right?
Mr. Robertson?
Yes.
On the circle, how did you get r equals 2? Or r goes from 0 to 2?
There we go. It should be 4.
Okay, thank you.
Okay. Too quick one, as always. Right. Let's see, is 5 anything interesting? Whoa. Whoa. What's the time like? Yeah, we've tons of time. I'm looking at 5 and it's scary. And I'm looking at 6. And it's nice. Do I want to do scary first and nice second? Let's do nice first and scary second. A version of 6 is that guy, right? And we're being told that this guy is e to the negative x plus y squared. And this guy here is e to the negative y plus x squared. So this notation is going to become this notation. Because we kind of need it that way, don't we, to be able to do it, right? So if you tell me f is this guy, they're just basically telling me the p and the q. So what I'm doing here is I'm translating the original fella, right, that one, and I'm recreating it as an e to the negative x plus y squared dx plus an e to the negative y plus x squared dy, right? In other words, I'm writing in a format that's going to make Green's theorem doable, right? If I just leave it like this, it's not really that helpful. So far, so good. Right, so essentially, there's my P and there's my Q, right? So those two guys go there. The region C is, I'll write it down, then I'll draw it. Y equals cosine x and it goes from the point negative pi upon 2, 0 to the point pi upon 2, 0. So let me draw that. There's negative pi upon 2. There's positive pi upon 2. And if you do the cosine, it looks essentially like that. And once you get to there, the instructions then say you come back home again, right? So, the sneaky little darlings. You're going from here to here, and then you're coming home. What orientation is that? Cosine.
Negative.
Yeah. So to fix it, stick a negative there. If I didn't notice the orientation there, wouldn't I get the right numerical answer, but it'd be the wrong sign? This is, it says y is cosine x going from here to here and then back home. So this represents our region D. So I should have all the pieces. Oh, well, I've got it here. I think this one lends itself quite well to a type 1 region, right? Vertical. X is going from here to here, so there's my limits of integration for x's. And it's not that difficult, isn't y going from 0 to the cosine? Are you comfortable about region D's limit of integration? Right, there's my shape, my loop. I want the shaded guy inside it. X goes from negative pi upon 2 to pi upon 2. A typical rectangle goes from the bottom 0 to cosine x. It should be ready for all the pieces then. So I'll leave it this version because it's easy to write. And it's going to be a double integral. And it's going to be from x equals negative pi upon 2 to positive pi upon 2. Y goes from 0 to cosine x. In here, we are going to be doing that guy, take away that guy. So I'll write it down. That way I don't need to keep moving around. And in this particular case, dy dx. So oops. It's going to be this integral to here, y from 0 to cosine x. If you differentiate this guy here with respect to x, all you get is 2x. And if you differentiate this guy with respect to y, all you get is 2y. And then this time, remember to subtract it. Are we good? Integral ready to go?
Do we bring the negative from because of the?
Yes, I missed it. After all that time and effort remembering it was there, I then go and forget to write it down. This guy is not that bad to do, but you are going to end up having to integrate a negative cos squared. Can you remember how you take care of cos squareds or 2 cos squareds or even negative cos squareds? How do we fix those guys for integration?
Substitute it for like the 1/2 thingy.
The 1/2 thingy works well because I know what you mean. That's the 1/2 thingy, right?
Yes.
Yeah. And then you do it, and it's probably not pretty. Oh God, I'm totally wrong. I'll trust them. According to what I've got in front of me, it's a 1/2 pi. I don't see it, but evidently there's going to be a whole load of things cancelling out or something. That's the only way around that problem. Now, the one I've been kind of, as you might have been detecting, is scared. It's a good way. Is 5. Right. The function is given in terms of that notation, which is fine. But we're going to be essentially converting it into the other notation in a minute. This guy is y cosine x, take away xy sine x, and that's just the p bit. And then it's going to be an xy plus an x cosine x, and that's going to be the q bit. Can you see why I was worried? That is one ugly looking vector function, isn't it? There's my P, there's my Q. And the region that we're going to deal with, I'm just going to draw it as they tell me. So it's a triangle. Oh, I should have read that word. It's a triangle. So you start at the origin and you go to 0, 10. And then you go to 2, 0. And then you come back home. I thought C was uglier when I scanned through it, but a triangle's not ugly, right? Triangle's easy to do. Right. There we go. So I'll set up my limits of integration. And so x is going to be from 0 to 2, and y is going to be from 0 to whatever the equation of that line is. 10 by 2 means it's a slopey -5, so that's -5x, and the intercept's at 10, so it's -5x at 10. What orientation are we looking at for this particular integral? Positive or negative orientation?
Negative.
Right. At least I'll remember it once. I may forget to write it in the next line. So it's going to be from x equals 0 to x equals 2, from y equals 0 to y equals -5x add 10. Now the scary part. Differentiate this guy with respect to x, take away, differentiate this guy with respect to y. Okay. Let's go for the first one. Where are you? If you differentiate this guy with respect to x, you'll get y. And if you do this guy with respect to x, you're going to have to do a product rule. So you're going to have to do a f-g and all that stuff. So here goes. So you're going to get a 1 times the cosine of x plus x times negative sine x. Then you're going to take away the other answer. Now, if you differentiate p with respect to y, you get a cosine x. And if you differentiate this with respect to y, you get a -x sine x. And that's why these guys get paid the big bucks, because something really nice, I think, is going to happen. Do you see this 1 cosine x? Won't you get killed off by that cosine x? Now, do you see this -x sine x? Doesn't it get killed off with this plus x sine x? So it wasn't scary at all. It was just y. That is kind of cool, now that I see it. Double integral, do your thing, remember the negatives there, you're good to go.
Wouldn't that be a plus because the 2 negatives?
Yeah, it's great. This one will be a plus, but that one's a negative, so they still kill each other off.
Oh.
Right, so this one here, the first loop is -x sine x, and this is plus an x sine x, so they kill each
Oh,
other
the
off.
circle just is making it look like a plus.
Oh, sorry. Oh, that one was not as scary. Actually, that one was less scary than the one I thought wasn't scary. So you sometimes you don't know, what's going to happen till you try it. Don't want to try that one. Yeah, we've got time. They're writing in that format, which is fine. The vector function is the square root of x squared plus 2. And the inverse tan of x. And region C is a triangle, so I'm just going to draw it using their instructions. And so, because they have no imagination, they're starting at 0, and then they're going to the point 1, 1, and then they're going down. Nope, then they're going down vertically. Forget that, it's not there. To there. Oh, it's a baby triangle. That's it there. I thought it was about there one. Well, limits of integration, type 1. We're going to do x's going from 0 to 1. And that's a straight line. Can't get much easier or simpler than the straight line y equals x. There's the limit of integration. I should put in the orientation here, so I'll go back. And yep, haven't they done another negative orientation on us? So this guy is going to be negative a double integral from x equals 0 to x equals 1, and from y equals 0 to y equals x. And our combinations are, there's my q, and there's my p. A little bit unusual, there isn't any y's mentioned, so that should be interesting when I come to do it. If you differentiate the inverse tan function, what's the derivative of the inverse tan? It's something you just need to memorize. What's the derivative of the inverse tan?
1/6 squared.
One over x squared plus 1. You were probably thinking integration in tan x and secant squared x, right? Which is a different thing, but not this thing, right? Take away, if you differentiate this with respect to y, don't you actually get 0? I think I'll take this one a little bit further because I'm curious to see what this looks like. If you integrate this with respect to y, you get y over x squared plus 1, evaluated at 0 and at x. Okay, you plug in x, you get this guy, and take away nothing. So that's how you're going to integrate. I was wondering what it would look like. What method will I use to do this, Christian? If you look at Mia, there might be a clue.
U sub?
And who's the U sub going to be? You're right.
X squared plus 1? Or
X
plus
squared plus 1, yeah, only guy in town. Don't overthink it. Sometimes things are what they seem, right? Yeah, U sub and off you go. So you're going to get a log in that answer because of that, I'm pretty sure. Oh, God in Himmel. Right, it's just I'm reading the question because sometimes lawyers get involved in these questions and I have to read them 3 times to make sense of it. Anyway, we're going to use Green's theorem to find the work done. Isn't the work done just a disguised version of find that? They didn't tell me to find that, but they said find the work done. So I know it's that. Right, we've seen that enough times. Now, the vector field that they're talking about is this fella, that fella. And we are going to be doing it on region C, which I'm now going to try and draw. And it's moving a particle from the origin, which is here, and moving it to 3, 0, which is here. Then along the line segment to 0, 3, and then back home. Oh, that wasn't that bad, was it? It was just a triangle after all. So, type 1, x goes from 0 to 3. Anybody want to have a shot at the equation of the sloping line?
Is it -1 plus 3?
You probably didn't notice, but you forgot to say the x. Agreed? Okay, so x is going to 0 to x equals 3, and y equals 0 to y equals -x add 3. It looks like we're doing an awful lot of triangles where you need to find the equation of a sloping line. So you might want to, you know, not talking too much, you know what you're doing, Mikey, but you might want to look into how you get equations of lines in general, right? And where are we off to now? This guy, take away this guy. So there's my P, there's my Q. So differentiate this with respect to x, I get y squared. Take away, well, actually, it'd probably be a good idea to write it like that, because when you differentiate this guy with respect to y, all you get is an x. You comfortable? That's a pretty boring double integral. None to see here. I get time for 2? Nope. I have time for 1, and tomorrow we'll finish off Green's theorem because we are going to be doing a century mass questions. Well, since we've done one of them, but not today. Let's finish on with a version of 9 then. Okay, a particle starts at the origin, so I guess I better draw the curve. Okay, so it starts at the origin, gotcha. And then it moves along the x-axis to 2, 0. Okay, gotcha. Oh, by the way, the one I just did, wasn't that a positive orientation? Right. So back to this one. You're going to here. Then along the quarter circle, x squared plus y squared equals 4. And then back home again. Couldn't you have just said a quarter circle in the first quadrant or something, and it would have been the same? Well, I guess you have to design the curve. Positive orientation, agreed? Now, since it's a bit of a circle, isn't that a candidate for polar? And so as far as polar is concerned, the radius here, I'll try and get it right this time, is 0 to 2. What will be the range of theta for this particular quarter circle?
0 to pi over 2.
Agreed. So it's going to be the integral from, I'll do theta, I think first, because I want to. And, oh, I forgot to tell you who F is. That is very important. Oh, it's just a sine X for the P guy. And the Q guy is, yikes, the Q guy is a sine of Y plus an XY squared plus a 1/3 X cubed. And we are going to do this guy with respect to X and take away this guy with respect to Y. Well, let's focus on this guy. If you differentiate this with respect to X, you get nothing from him. You get a Y squared. And you get, oh, an X squared. That wasn't too bad. Take away, well, if you differentiate P with respect to Y, you get a big fat 0. And it's going to be R dr d theta, which looks like it's going to come out really nicely. Take away nothing doesn't change that. What's X squared plus Y squared look like in polar form?
Is it R squared?
And that one gives me another one, so it's now R cubed. And would you agree that's a nice variable separable? Off you go and you're done. Right. Damn it. Okay, I cannot do, because it's take too long and we'll do it tomorrow, the centre mass question, but we can talk a little bit about it. So if you want to find the centre of mass of an object, you can find these two separate line integrals. You see them? And all you need to do then is essentially find that guy and then do that guy. Won't both of these turn into double integrals? This fella here, is he P or Q? It says X squared dy. Is that P or is that Q?
Q.
Q. Technically speaking, don't you have 0 dx's plus X squared dy? Does that help? Right. And when you do this one,
That should be a dx. According to the homework.
oh, yes. So what's the dx? Sorry.
Or the second one. The
Oh,
that. Thank
yeah. God, I wrote that down, bro. And so well, you could almost guess it should be that. So what you're going to get here is y squared dx plus 0 dy. We know how bad finding centres of mass are. I hope you're going to find that using Green's theorem makes them from horrible just to bad, right? They're not going to be easy, but they'll be less horrible than they would be. If you were trying to do the centre of mass of this same question the old-fashioned way, it's pretty messy integration, right? Because line integrals are really, if you do them by converting everybody into t's, aren't they quite time-consuming and could be quite messy. So when we come in tomorrow, I'm going to say to you, because I will have forgotten, which question were we going to do?